All right, let's go ahead and get started. Just a reminder, so Monday is the next test. If you didn't look at it last time, there is basically this course has its own website, and I think probably the most valuable thing you can review is the practice tests on here. So math.asu.edu/MAT242. I haven't looked at the second one until just now, but the first one was, there's another 24-page document. So again, I don't know if it's worth your time to do every single thing in here, but to like diagnose where you need to review, I think it's at least a good place to start. So if you haven't already been there, please go check it out. All right. Any questions before we get back into eigenvalues? All right. So I think we ended yesterday. We did a bunch of examples where we found the eigenvalues of 2x2 matrices, right? Let's do a larger one now. Oh. So remind me, how do we find eigenvalues? How do we identify them? Right. So I want to find the determinant of this related matrix A minus lambda I. What's that determinant going to be? How do we find the determinant of a 5x5 matrix? What do we have to do?
Do the diagonals and triangle.
So that's a very valuable thing to realize here, is that this thing is already in upper triangular form. So because of that, what is the determinant? Not quite, because so if I was finding the determinant of A, yes, it would be 1 times 2 times 3 and so on. But I'm finding the determinant of this new matrix that I actually haven't written down yet. So maybe I should do that. Instead of going straight to this determinant, what does this matrix look like? It should be 1 minus lambda, 2, -3, 4, -5. Anything that's a 0, I'm going to just leave off for now. And then I promise that's an accepted way of shorthand to show there's just zeros beyond that border. So one thing we've talked about a while ago was that the determinant of a matrix that is upper triangular or lower triangular, you can get by just multiplying all the diagonal entries together. So then what is the determinant of A minus lambda I? All these factors, and I am not going to distribute them until, well, maybe we don't have to at all. So this determinant, what do I want to do with this? Set it equals 0. How can I find my eigenvalues from here? You can set each one of these things equal to 0, right? Since I multiply these 5 factors and their product equals 0, then this essentially I can set each one of them individually equal to 0. So what are my eigenvalues? 1, 2, 3, 5, 8. So this is a direct consequence of the fact that the determinant of an upper triangular matrix is just the product of all those diagonals. If you have an upper triangular matrix, its eigenvalues are simply what shows up in the diagonals. So otherwise, this would take an awful lot of work to expand all these minors and cofactors from a 5x5 matrix and get all those smaller determinants, but keep an eye out for these kinds of shortcuts. Questions there and why we're allowed to skip all the expansion by minor stuff. All right. Let's end with one that's not 2x2. So I want to find the eigenvalues, or what I'm asking for is a basis for the eigenvectors, but that comes directly from, I can't get the eigenvectors if I don't know what the eigenvalues are. So I got to get those first. So that comes from this A minus lambda I. So no zeros this time to rely on. So how can I find the determinant of this thing? Got to do expansion by minors, and we have a lot of choices. So what do you want to expand on? I think we have a total of 9 options, or 6. Sorry, what's that? Are we going to expand on the first column or the first row?
I guess first column and first.
We have to pick one. So maybe we might be talking past each other. We might be talking about different things. We're eventually going to have to, like, let's say it doesn't matter if you're going to expand off the first column or first row. Your first move is going to be to delete that. So I guess the difference would be, well, let's just build this out. What does minor 1, 1 look like? It looks like 5 minus lambda, -3, 12, -7 minus lambda. From your point of view, what's the next minor we would need? 1, 2. Okay. So that sounds like we're expanding off the column. No worries. They're just, I'm being pedantic, but I kind of have to be. So -6, 3, 12, -7 minus lambda. And then finally, I'm not doing what I'm writing down, am I? No. Is this more honest? Okay. Sorry about that. So then this would be -6, 3, 5 minus lambda, -3. So these are all the minors I need. So expansion by minors off of column 1. So now that I've pulled those minors out, what do I do with them? Okay, what's the determinant of the first one? So these are all 2x2 matrices, so we can, I mean, this is really the only way we know how to take a determinant directly, is matrices of this order. So plus 36. Okay. Do we agree with what I've done? me double check it. Okay, so I think those, unless you see any errors, I think those are all good for the determinants of those three minors. But now what do I have to do with them? Okay, so I have to check to see if some of these I have to might have to negate, right? Are there any of these that I have to multiply by -1? This should just be this one, right? So just to remind you, -1 to the power of 1 plus 1. So the only one that's going to make a real difference is the middle one. So from there, let's write out what we have. 5 minus lambda minus 7 minus lambda. So I'm going to get plus 36 plus 18. I feel like I must have made a mistake. Unless you're all okay with that. I'm most worried about sign flips, but I feel like I was careful. So if I look at the constants, I should have a 36 and an 18. Those are both positive. But then I have a -36, which should have been flipped to a positive, right? I don't know if I agree with this 72. Does that make more sense? 36 plus 36 plus 18. Okay. All right. So what can we do from here? I think we probably have to actually expand. So lambda squared plus 7 lambda minus 5 lambda plus 2 lambda minus 35 plus 90. There's something very huge that we all forgot, including me. Yep. Yep. So I should multiply minor 1, 1 by what? 2 minus lambda times -5 minus lambda, -7 minus lambda, plus 36. And then plus -3 times -1. So really just plus 3 times 42 plus 6 lambda minus 36. And then -6 times all this. 18 minus 15, that's 3, plus 3 lambda. Okay, so sorry about that miss, but I think we're back on the right track now. We have a 3x3 matrix, so how many eigenvalues should we be looking for? Should be looking for 3. So the thing that tipped me off is the fact that I was not going to get a lambda squared out of any of this. Any question about how we got to where we are so far? Okay. If it's okay with you, I'm going to, since I'm running out of space and I want to get to the eigenvector part of this, I am going to, does anybody here ever watch cooking shows? Where they start something and then they just flash forward to the end? Let's do it. And I think you said your calculators could not deliver eigenvalues, right? Is that true? Okay. Okay. You could probably find the code. Okay. So we got lambda equals 2, -1, -1. So there's no, the eigenvalues are not guaranteed to be different, but there will always be 1 for each row or each column, depending on how you want to look at it. In this case, 2 of them are the same. So I believe strongly, I know we can solve equations, but let's kind of flash forward to this. And the reason I want to do this is I want to show you a set of eigenvectors that whose basis is a little bit different. So let's start over from here. These are my eigenvalues. How many different eigenvectors do I have to find? It's going to be 2. I mean, it's going to be repeated. So let's go ahead and find eigenvectors. So how do I find the eigenvectors that go with lambda equals -1? Right, so I'm going to do this. A minus -1i, or a plus I, gives me this. 3, -6, 3, -3, 6, -3, -6, 12, -6. And we're going to find a basis for this column space, essentially. Or this, sorry, this null space. So how do we do that? Right, I can start reducing rows. What's a good step to do that? Anything jump out at anybody? I'm going to do that to everything. 1/3 of A goes back to A. Or I'll just call this N. A is the thing we started with. So if we do that, I get what? 1, -2, 1, -1, 2, -1. Actually, let's do this. 1/3 of row 1 to row 1. 1/3 of row 2 to row 2. 1/6 of row 3 to row 3. Then I get -1, 2, -1. All right, from there, what do we find out? Yeah, so row 2 and row 3 are identical, right? Which means I can add those together and get that. But now row 1 and row 2 are opposites, which means I can add those together and get that. So I'm taking some kind of liberties doing all my operations in one step, but hopefully that's okay. If I need to, are you okay with me telling you this is the only row that survives? Okay. Now, how do we build a vector based on that? What does this top row tell us? X1 equals 2x2 minus x3. So how many parameters do we need? Should need 2. So let's see what a vector looks like. X1, x2, x3 equals what? Well, we said you need 2 parameters, so let's call them, I'm just going to leave them as x2 and x3. What's the vector multiplied by x2 look like? I don't think it should be, 2, 1, 0? Oh, okay. So why is there a 2 in the first entry there? Okay. Probably makes more, let's do it row by row. That might be a little more intuitive. X1 is equal to 2x2 minus a single x3, right? So I like that top row. What does x2 equal? It's a parameter, so we're just going to basically say x2 equals x2. x3 is going to be kind of similar, right? x3 equals 0 x2s plus 1 x3. So then what's a basis for this, for the eigens, like we call this the eigenspace, the vectors that make up the basis for this eigenvalue? So what's our basis for this eigenspace? It's not 1, 1, 1. The basis is going to be these vectors that are multiplied by our parameters. Because I'll just a reminder here, x2 and x3 are real numbers. And I'm multiplying those real numbers by these 2 vectors. So basically by letting x2 and x3 take on the value of any real number, and then adding those vectors together, I'm generating all the linear combinations. So that's what a basis does. And a basis can be totally defined by whatever those vectors are. So here's the basis for lambda equals -1. How are we doing? So I think this is the first eigenspace we've looked at whose basis had multiple vectors in it, which is absolutely possible. Let's build one for lambda equals 2. So what does the matrix look like that I'm trying to deal with there? You said it's 2 by 3? Okay, yeah. Right, so yeah, the order is never going to change. And what's this going to look like? Why does that become 0? Okay, so I am subtracting 2 from all the -3, 3, -3, -6, 12, -9. One thing I noticed I can reduce right away is this 0, -2, 1, -1, 1, -1. All right. Where should we go from here? How come? What are you trying to do with this matrix? Do you want to do it the fun way, or do you want to use a calculator? You want to do a calculator, do it. I want to make sure you feel comfortable with it for Monday. So what's important to me is that you know that you need to reduce right here. And if you can rely on the robots to do it for you, let's do it. So what's the reduced row echelon form?
1, 0, 1.
1, 0, a half. 0, 1, negative 1 half. Okay. Someone said they got the identity. Give a sign flip. Okay. Or I'm assuming it's a sign flip because I do that all the time. If this is what our reduced matrix looks like, what does this tell us about our vectors? The vectors in our basis. X1 equals, there we go, negative a half of X3. X2 equals a half of X3. So how many parameters do we need? Just one. So X1, X2, X3 is equal to X3 times what vector?
Negative 1 half, 1 half.
Negative 1 half, 1 half, 1. So then the basis for this eigenspace is how many vectors? Just one. And I might choose to write this vector like this, negative 1, 1, 2. Neither one of these is wrong, though. These are both fine. I just like having whole numbers if I can help it. So again, just a reminder, eigenvectors are not unique. Oh, I did? Sorry, go ahead.
So like, could you explain to me like why we could write it like negative 1, 2?
Yeah, absolutely. So eigenvectors are not unique. There's an infinite number of eigenvectors that are correct. The thing you have to respect is that the ratios between the entries in that matrix or the entries in that vector fit what this tells you.
Okay.
So essentially what I did, I just doubled both these equations. So I got 2x1 equals negative x3, 2x2 equals x3. And again, that's totally personal preference. I could have, this is also a good eigenvector, minus pi, pi, 2 pi. There's no good reason to do that, but that also fits the conditions that we found by reducing the matrix. So you can scale your eigenvectors however you want. A pretty common thing is I think we found a couple eigenvectors last time that were 1, negative 1, or vice versa. I forgot I didn't annotate anything on these slides, but I know this vector showed up a couple of times. There's no reason not to use this vector. I don't think one is any more simple than the other. So you have a lot of choice there. Just make sure that whatever the way you parameterized your reduced matrix, that has to fit with whatever you come up with. How we doing? Go ahead.
So when we were finding the eigenvalues, would you be against, like, once we get into its final form, would you be against us putting it in the graph calculator, like with x, the variable, to get like where it hits the x-axis?
Oh, I see what you're saying. No. Actually, ask me again. I want to make sure I'm following you. Okay, so at what point in this process would you project? Okay.
So when you multiply.
Oh, I see. Okay. Yeah, you can solve that equation using a graph calculator or whatever. The only thing that we don't allow is if your calculator has like a symbolic, like CAS equation solver. We say no to those things, but yeah, if you were to replace all these lambdas with x's, graph it, and find the roots, that's perfect. That would also find. The only thing I'll caution you about is it would only find 2 roots. So would you know how to recognize from a graph that -1 is actually a double eigenvalue? It doesn't cross over. It's going to be tangent to the x-axis. So that's the thing to watch out for. Good question. What else? So real briefly, what this probably looks like if you were to graph this is, so I know I have eigenvalues at -1 and +2. It might look something like this. I'd probably have this kind of relationship where it touches the x-axis at -1, and then at 2, it crosses through. It could either look like that or reflect over the x-axis, but I'm very confident that it touches the x-axis at -1 without crossing, and it crosses at 2. If I want to go into detail about how I know that, I can remind you, but it's not really it would take a long time for right now, and we got other things to get to. What else? Before I put 5-1 away. Okay. We're going to try to open up a new slide without losing connection. All right. So let's talk about this idea of diagonalization. So basically what diagonalization is, we're going to try to take a square matrix and break it up into the product of 3 matrices, one of which only has entries on its diagonal. Might seem really arbitrary to do that, but let's talk about why we want to do that. So let's start with a 3 by 3 matrix, and let's define that characteristic polynomial. How do I find that characteristic polynomial? Don't need to do expansion by mind. Did I not mention this term last time? The characteristic polynomial? I obviously showed it to you, but I might not have called it that. So basically what this is this, the determinant of a minus lambda I equals 0. So setting up that determinant, setting it equal to 0 will always give you a polynomial in lambda. So essentially that's what I'm asking for here. Can I find this determinant? I can, but I should probably write this new matrix first. Because what's the determinant of A? Like without making any kind of alterations to it? 0, how come? It has a full row of zeros. So if I expand on that row, I'll just multiply 0 by all my cofactors. So -2 minus lambda, -10, 4, 0, negative lambda 0, 1, 5, -2 minus lambda. What the heck is that? Anybody else hear that? Okay. Yeah. We're not that close to the ground. Okay. All right, how should I get the determinant from here? Middle row? Middle row is a really good choice. How come? There's 2 zeros. We're only going to deal with 1 minor. So let's do expansion by minors on row 2. Not used to my teeth vibrating in class. All right. So how do we expand on that row? How many minors do I need to make? Just the one, right? Which one do I need to make? the minor off of 2, 2. That matrix looks like this. Minus 2 minus lambda, 4, 1, minus 2 minus lambda. And the determinant of that is minus 2 minus lambda squared minus 4. So then how do I get the full determinant of A minus lambda I? Right. So minus lambda times minus 2 minus lambda squared minus 4. Do I have to multiply by -1 or am I okay? Okay, I think this should be good. So this is the characteristic polynomial. Before we do any kind of expanding to it, this is what it looks like. But let's go ahead and expand it. So minus lambda times whatever happens in here. Lambda squared minus 4 lambda minus 4? No, plus 4. Plus 4. Oh, so convenient. Minus 4 equals 0. So I get minus lambda cubed minus 4 lambda squared. That's it, equals 0. Okay, so I think this is as much as I care to flesh this out. Lambda cubed plus 4 lambda squared equals 0. We okay with how we got there? That's something we can solve? Okay. Let's go ahead and solve it while we're at it. We're going to have to eventually. How do we solve this? Factor out lambda squared, and then I get lambda plus 4 equals 0. So then what are my eigenvalues? How many should I have, by the way?
3.
Should have 3. Do I have 3? What are they?
0, 0, minus.
2 of them are 0. So I got lambda squared equals 0. And then the other one's minus 4. Questions on how we got there? Good question. So that all comes from the power on lambda here. Yeah. So if I really wanted to break this down further, I could write this as lambda times lambda plus 4 equals 0. So in squaring that, you kind of hide the fact that there's a third factor there. But 2 of those factors equal 0 when lambda equals 0. So we have a repeated eigenvalue. And then with -4, I only have one factor that yields that eigenvalue, so it has a multiplicity of 1. So that's one thing I want to talk about, or 2 different kinds of multiplicity. One I know you've dealt with, one is probably brand new to you. So probably when you took algebra 2 for the first time, and probably a few times since then, you've probably heard about the multiplicity of the root of a polynomial. It's essentially, if you were to factor out a polynomial and set it equal to 0, how many times does that factor appear? So that's the algebraic multiplicity. So if I go back to what we did here, lambda equals 0 has an algebraic multiplicity of 2. Lambda equals -4 has an algebraic multiplicity of 1. The geometric multiplicity is this thing that I'm relatively sure is brand new to all of you. So every eigenvalue has a geometric multiplicity, and that refers to how many vectors are in its eigenspace. So what's the dimension of its eigenspace? So one of those we just found. The other one we got to deal with still. How are we doing so far? All right, so we found all the eigenvalues. So lambda equals 0, that's multiplicity 2. And then lambda equals -4, which I'll not give the multiplicity of because 1 is basically a default. So how do I find the basis of each eigenspace? Which one do I want to do first, -4 or 0? 0 sounds good. So what does that mean I do from here? You leave A as is. It's going to be A minus 0i. So the fact that lambda equals 0 is an eigenvalue means that I didn't really have to do anything to A to make it linearly dependent. Does that make sense with the way A looks? What does it mean for two rows to be linearly dependent? One's a linear combination. So 0, 0, 0 is a linear combination of any vector you can think of, because 0 times a vector is an acceptable combination. So that row is already dependent on everything. All right, so we're making a basis for the eigenspace of this. Where can we go from here? Reduce. What's a good move to reduce this thing? Half the top row, so 1/2 of row 1. We'll just put that back. -1, 5, 2. I did something wrong. Just dropping signs. 1, 5, -2. Now what? Yep. Row 1 plus row 3. Which one do you want? And put it where? Row 3. Okay. Well, then that makes this 0, 0, 0. I think we're done reducing. So what have we learned? X1 equals 5x2 minus 2x3. I think we have a flip here because the first one is negative. So I think this is okay. So how many vectors are going to be in this eigenspace? 2. How do you know that? 2 parameters. So the number of parameters will always be in step. It will always be the same as how many vectors are in your eigenspace, the dimension of the eigenspace. So x1, x2, x3 equals something times x2 plus some other vector times x3. All right, what does x1 equal in terms of x2 and x3? -5, +2, yeah. And then x2 equals itself, and x3 equals itself. So the basis we have for this eigenvalue is negative 5, 1, 0, 2, 0, 1. Questions? Yes. Because let's remind ourselves how we find eigenvalues. How do we find eigenvalues? Basically, we set the determinant of not A, but something related to A equal to 0, right? But in this case, what's the determinant of A? 0. So I already don't have to. This thing already has a determinant of 0 without me subtracting the eigenvalues from that diagonal. So yeah, you're right. If you see a row or a column that's all zeros, you can already assume that 0 is an eigenvalue. What you can't know necessarily is what the multiplicity of it is, or what the other eigenvalues are going to be. But yeah, it's a dead giveaway that you're going to get a 0 for an eigenvalue. All right. Now what do we have to do? Right. So now let's construct A plus 4i to negative 10, 4, 0, 4, 0, 1, 5, 2. Okay. It seems like I have sign flips, but I don't think I do. Okay. All right. So what should we do from here? Right. We can cut the first row in half. Okay. Now what? Row 3 minus row 1? Okay. Row 3 minus row 1. Back to where? Okay. I have 2 rows where the only non-zero element is the middle. What does that mean? They're both essentially 0, 1, 0, right? So here's what I'm going to do. I am going to keep the first row, call the second row 0, 1, 0, and get rid of the third row. So basically we're taking a couple shortcuts. We know that 0, 4, 0 and 0, 10, 0. One of those is a multiple of the other. You can also scale them both down to where they're both 0, 1, 0. And since you have a duplicate row, you can just subtract it from itself. Now what do we have? Is there any more reducing we can do? I think there's exactly one more thing we can do. What would that be?
Add 5 row 2 to row 1.
If we add 5 of row 2 to row 1, what happens? So now are we done? Should be. Okay. So now that we have our fully reduced matrix, what have we learned from it? X1 equals minus 2x3. X2 equals 0. And x3 equals what? Well, x3 is, I mean, basically we're letting x3 be a parameter, right? So this is going to be x3 times negative 2, 0, 1. So what's the dimension of the eigenspace for lambda equals negative 4? Just 1. How are we doing so far? Does it look any different than what we did in the last section? Okay. So here's what diagonalization is. Go. Meant to animate this, but here we go. So a matrix is diagonalizable only if this is true. If these two multiplicities are equal. So just a reminder, algebraic multiplicity is how many times that how many times that each eigenvalue is repeated. And the geometric multiplicity is how many vectors are in the basis for that eigenspace. So without thinking about what the heck diagonalization is or how we do it, let's see if the thing we've been dealing with is diagonalizable. What's the algebraic multiplicity of lambda equals 0? 2. It should, like, when we set up the polynomial, we got lambda squared equals 0. How many vectors are in its eigenspace or in the basis for its eigenspace? 2. So that matches. This has to be, so that has to match for every single eigenvalue you have. We're good so far. What's the multiplicity for lambda equal negative 4, the algebraic multiplicity? 1. It showed up in the polynomial once. And how many vectors are in the basis for its eigenspace? 1. So we can diagonalize this. So that's what we're going to do next, but let's talk about how to do it. So basically what diagonalization is we take A and we break it into 3 different matrices that we're going to multiply together. So let's talk about how to make the matrices P and D. P is made from all the vectors and the bases for each eigenspace. So how many total vectors do we have in all of our eigenspaces here? 3. What D has in it is the only entries in D that are not 0 are along the major diagonal. So basically where the row number and the column number are the same. And what's in that matrix are the eigenvalues. So the only thing we have to be really careful about is that, we match those things up correctly. For example, I don't want the vectors that go to lambda equals 0. I don't want to correspond them to the vectors that go with lambda equal negative 4. So this is kind of a recipe for this decomposition, so let's actually do it. So we're going to break A into PDP inverse. How big do each of these matrices have to be? Or what's the order of all of them? They're all going to be 3 by 3. So the way we make P is it's going to be the columns are going to be the eigenvectors we just dealt with, or the basis vectors we just found. And if you got your notes, tell me what they are. In any order you want, really. Negative 5? Negative 5, 1, 0. 2, 0, 1. Negative 2, 0, 1. Good. Then what D is going to be is mostly zeros. But what's going to go along the diagonal here are the eigenvalues that fit here. So the column 1 of P you just gave me, what eigenvalue does that go to? 0? How about the second one? And the third one? So that's D. And then what's P inverse? It's based on P. When you got an inverse repeat, let me know.
Okay, 0, 1, 0,
0, 1, 0.
1,
Well, sorry, what? 1/4,
5,
1/4, 5/4, 1/2.
the bottom of -1, -5, 4.
Negative 1/4, negative 5/4. And then 1/2. So if we did this correctly, then P times D times P inverse should be the thing we started from. Cool. So for right now, we're going through the nuts and bolts of how to do this. So I haven't really given you the why we would ever want to break these apart yet. For now, I'm going to hold back on that. Are we okay with the process so far? How we did this, and why we knew we were allowed to do it. All right, shall we go again? Let's do this. Let's find out if this thing can be diagonalized. So how do we answer that question? I need to find eigenvalues because the answer to that question comes from eigenvalues and eigenvectors. So I better find those. So how do I find eigenvalues of this thing? Yeah. All right. Got to set up this equation. How can I find the determinant of this thing here? Right. So I think we're going to have to do 3 minors no matter what we choose. So what do you want to expand on? Row 2? How come? Smaller numbers are better, yeah. So then what minors do we have to make? 2, 1, 2, 2, 2, 3. Oh, oh yeah, like the whole point. Did I forget the whole point? Yeah, I did. So for 2, 1, row 2, column 1, that'll be 8, negative 10, 3, negative 4 minus lambda, right? And then for 2, 2, Then for 2, 3, 5 minus lambda, 8, 2, 3. This determinant is equal to 8 minus 4 minus lambda plus 30. And then I think I have to multiply each one of these by -1, right? What's that? Sorry, I was writing these out. I ignored the middle one. Yeah, you're correct. I didn't represent what I was trying to say very well. What's that? Yeah, and multiplying by the corresponding entries, right? We okay if we do the MATLAB thing again? Sorry. Weird. They're not imaginary. Why are you telling me about it? Okay, so what eigenvalues did I get? I got 3 and 3, 0, 0. So do we know yet if our matrix is diagonalizable? How do we find that out? Okay, so one of these is going to be a minus 3i, right? So what does the eigenspace look like for a minus 3i? So 2, 8, -10, 1, -1, 2, 2, 3, -7. What does that reduce to?
I think the one and two in the second row.
The 1 and the 2 in the second row?
Yeah, the one in the first column, second
Oh.
row.
Oh yeah, I crossed them all out up here. And since I closed the presentation, I can't erase it now. So how's this reduce?
Here's the identity.
You got the identity? That means I did something wrong then, because the eigenvalues are supposed to tell you when it's linearly dependent. So 5 minus 3 is 2. Is the entire row? Maybe I should just do this. Yeah, I did something wrong. Nope, because I think I put this into MATLAB correctly. Let's make sure. Oh, I absolutely. So think of all the ways you could have screwed this up, and I did all of them. So -1, man, I flipped all the signs. 5, 8, -10. -1, -2, 2. 2, 3, negative. Okay, that's better. A. Let's just put the last 10 minutes behind us. So what do we get? Just -1 and 2 zeros? Okay. Lambda equals -1 gives us this matrix. 6, 8, -10, -1, -1, 2. 2, 3, -3. All right, now let's reduce this actually relevant thing.
-3, 0, 1, 1.
1, 0, -3. The next row is what? 0, 1, 1. Zeros. What is the basis, or can I find a basis for this eigenspace now? Let's do it. What does x1 equal? x1 equals 3x3. x2 equals -x3. And x3 is just a parameter. Like that. All right, so is A diagonalizable? Yes, no, maybe. Still maybe, right? So we haven't gotten any roadblocks. So what was the algebraic multiplicity of lambda equals -1? Most of its geometric multiplicity. Okay, because we got one vector in its basis. So now let's do this. Lambda equals 0, which means we want to reduce A. So someone do that for me. Is the identity? That can't really?
Go 1, 0, -2, 0, 1, 0,
1, 0, -2. One more time.
0, 1, 0.
0, 1, 0. So what's the basis for this eigenspace? Is it only one vector? What's the parameter? X3 again? 2, 0. Can A be diagonalized? Yes, no, or maybe. Now the answer is no. How come? How many vectors should I have just gotten in this basis? If I was going to be diagonalizable, I should have gotten 2 vectors. So unluckily, we went looking after lambda equals -1 first. So the answer is no.
Is it always going to be a coin flip on which one will be, or to like a
I don't, if there is a way to kind of intuit which one is going to be the problem, I don't know what it is.
So we recommend finding the eigenvectors and like, if you have so for example, we had 0, 0.
Yeah.
Say we had 1, 1.
Uh-huh.
Possible.
It is possible to have, so any eigenvalue is like, so let me put it to you this way. We can take an existing square matrix and diagonalize it if all the conditions match up. But I can define P and D however I want and multiply them together to make a diagonalizable matrix. So if I make that matrix D 1, 1, 1, then I will build something that has an eigenvalue of 1 repeated 3 times. So yeah, I can basically construct anything I want with whatever eigenvalues I want. Good question. All right. Have a good day. I'll